Let us explore the ripple carry adder. In this video, we'll delve into the concept of multi-bit binary addition. We will discover how to build multi-bit adders by cascading full adders. Let's quickly review the full adder. This table illustrates the truth table of a full adder, which takes three inputs, A, B, and carry in, and produces two outputs, sum and carry out. Here are the logic equations. The sum is equal to a XOR B XOR carry in. The carry out is equal to A and B, or carry in and a XOR B. The core idea behind a ripple carry adder involves cascading multiple full adders. The carry output of one stage becomes the carry input of the subsequent stage. In this diagram, you can see the carry propagation flow. We have full adder 0, then the carry moves to full adder 1, then the carry moves to full adder 2, and finally the carry moves to full adder 3. Full adder 0 is the least significant bit, and full adder 3 is the most significant bit. This is the structure of a 4-bit ripple carry adder. The diagram consists of 4 full adders: FA subscript 0, FA subscript 1, FA subscript 2, and FA subscript 3. These adders are connected in a chain. The carry output from one full adder is fed as the carry input to the next full adder. The least significant bit is bit 0 and the most significant bit is bit 3. Note that the carry in to the first full adder FA subscript 0 is C subscript 0, which is 0. Let's see an example. We are adding 1011 base 2 plus 0110 base 2. In decimal, this is 11 plus 6. The result is 10001 base 2, which is 17 in decimal. Here is a step-by-step breakdown of the carry propagation. For bit 0, 1 plus 0 equals 1, and the carry 1 is 0. For bit 1, 1 plus 0 equals 0, and the carry 2 is 1. For bit 2, 0 plus 1 equals 0, and the carry 3 is 1. For bit 3, 1 plus 0 equals 0, and the carry 4 is 1. Here's the Verilog code for a 4-bit ripple carry adder. The module is named ripple_carry_adder_ for bit. It takes two inputs A and B, each 4 bits wide, and a single-bit carry-in CIN. It outputs a 4-bit sum and a single-bit carry-out COUT. Inside the module, we declare 3 wires, C1, C2, and C3 to represent the internal carry signals between the full adders. The code instantiates 4 full adder modules named FA0, FA1, FA2, and FA3, connecting them in a ripple carry configuration. Each full adder takes the corresponding bits from A and B, the carry-in from the previous stage, and outputs the sum and carry-out for that bit position. Let's analyze the timing and characteristics of the ripple carry adder. The total propagation delay, T subscript total, is equal to n multiplied by T subscript FA, where n is the number of bits and T subscript FA is the delay of one full adder. Therefore, for a 4-bit adder, T subscript 4-bit is equal to 4 multiplied by T subscript FA. The worst-case scenario is when the carry propagates through all stages, which is the longest path. Key characteristics of the ripple carry adder. It has a simple implementation. It is slow for large bit widths. It has a low hardware cost. It has a linear delay with bit width. There is an area versus speed trade-off. Here are some applications of the ripple carry adder. They are used in simple processors and microcontrollers, low-power embedded systems, basic arithmetic units, educational demonstrations, and they can be a building block for complex adders. Key points to remember. The ripple carry adder uses cascaded full adders. The carry ripples through the stages. It has a linear delay with bit width. It is a simple but slow design. And it is a foundation for faster adders. In conclusion, the ripple carry adder is a simple, cost-effective solution for multi-bit addition. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.